All right, we have another example here. Gravel is being dumped. This is sort of another classical one, dumped from a conveyor belt at a rate of 30 cubic feet per minute, and we get a right circular cone. So, okay, here's my conveyor belt, and it's dropping stuff, and it's forming this nice conical pile. Okay, and so that's coming down here at a rate of 30 cubic feet, so feet cubed per minute. And we get a right circular cone. Okay, so there we have that. And we have a nice radius. And we always know that the diameter is twice the height. Okay, or put differently, twice the radius is twice the height, so radius is equal to height. Whew, we'll use that later. All right, how fast is the height of the pile increasing when the pile is 10 feet high? So we know that at this specific moment, or at a specific moment in time, height is 10. Okay, and so let's start to kind of make our list of what we know and what we don't know. So we know that the height at a specific moment is 10. We don't know necessarily how fast it is increasing. We know that the radius is going to be the same as the height. So in this case, it would be 10. And we don't know what dr dt is, so we don't know how fast the rate of or how fast the radius is increasing. Okay, we'll get there though, I promise. Okay, and lastly, we know that the volume, okay, we don't know what the volume is, we can figure it out, but we know that the change in volume is this 30 cubic feet per minute. Okay, so for the volume of a right circular cone, I believe that we have the equation volume is equal to 1/3 pi r squared h. Okay, but now, okay, so then I can find the volume at this specific moment in time. At this specific moment in time, this would effectively be volume is equal to 1/3 pi, and then radius is the same as height, so it'd be 10 squared times 10, which is effectively 10 cubed, right? So I'd have 1,000 pi over 3. Okay, but now I think this realization that radius is the same as height actually can impact my equation. Instead of having it as 1/3 pi r squared h, I can recognize that, okay, well, radius is always the same as height, given that the diameter is twice the height. So radius is the same as height, and I'm really interested in dht, how fast is the height increasing? So I'm just going to say that in my equation, I'm going to have pi r h squared times h, or effectively h cubed. Okay, and this is the equation I'm going to use because we always have the relationship that radius is the same as height. So with that, I'm going to introduce a time derivative. Okay, differentiate v with respect to time, we get dv dt. And then differentiating this result, it'd be 3 times 1/3, I'll write it out, 3 times 1/3 pi h squared times, now the derivative of h via implicit differentiation. And then in step 6, I have to substitute and solve. So in step 6, I have to say dv dt is 30. And then we have these two canceling out. So I'd have pi times h squared, so 10 squared times dh dt. And then if I solve, this just gives me that dh dt is 3 over 10 pi. Okay, so then I'm going to say in this case the height of the pile is increasing at 3/10 pi feet per minute. And we're done. Okay, so again, here it was getting the diagram, and then the only thing that was really different here was we were given the fact that we were given some relationship between radius and height, so we could eliminate one variable as needed and work with just two variables instead.